then I start introducing the main topic for today's presentation, machine transfer learning method that we use it in our recent work. And at the end, I will summarize. So let me start from something very simple. So I talked a lot about correlation entropy and which is related to the correlation matrix and so on. But deep down, everything is related to correlators. We all took our quantum mechanics course at some point, and we know what correlators are. So um, the correlators define it, as you can see in the screen, basically means you're uh, annihilating an electron at site J with some spin, and then you creating that's another electron at site I with some spin. So, which means you're basically moving a spin from in your system from one side to the other. But in the same sense, if this site index are equal, which means nothing but the number of operators that we all know about this. So why this is relevant? Because quantum systems, especially in terms of fermionic systems, uh, we have different quantum phases. We have metals, we have insulators, we have superconductors, ferromagnets, and so on and so on. So correlators, these kind of correlators will behave differently in different quantum phases. For example, in metals, electrons can move more freely than in the insulators, and in superconductors, it's a whole different story. So this is why this is the correlators, the definition, the concept of correlations are very relevant thing. So how do we solve these correlators in terms of in real space, in terms of in many-body physics? We use this method, call it density renormalization group theory. If you want to solve your many-body Hamiltonian in real space, which is fine, you can code and solve theoretically with that method is called exact diagonalization. But if your system is, let's say, above 10 side, 12 side, that the dimensionality of your Hamiltonian will explode quickly. So in the 90s, in 1990s, people thought about this new idea that we don't have to know the Hamiltonian in the whole Hilbert space. We need to know what is relevant. So they thought that maybe we can assume that the eigenfunction of the Hamiltonian as a product of matrices, as you can see in the screen, which its dimension is much smaller than the full Hilbert space. And you can understood this as like you're multipartite in your system. If you have just bipartite your system, that the eigenfunction can be just a product of two matrices. And there is one important notion also comes in. So when you say, let's say, for example, M1 matrix M1 times matrix M2, so there is a dimensionality involved. If M1 is 3 by 2, then M2 has to be 2 by 3, and this is called a bond dimension. So if the system is more entangled, then if there is more entanglement in the system, then you need more bond dimension to represent the many-body system with this method. So in that sense, if you think about one-dimensional system and but just the simplest case is you bipartite your system, and then this subset of your system is only connected. If you imagine a one-dimensional chain, this two subsystem is only connected by a point, which means the entanglement, according to the area law, the entanglement is there is a maximum value for the entanglement, and then even your system will increase to infinity. This the entanglement of the entanglement involved in your system wouldn't be affected that much. So, which means this method is especially useful for one-dimensional system, and then it has been developed a lot we use this DMRG method to solve our many-body Hamiltonian. So, and then let's just start to have a look on the simplest many-body Hamiltonian, which is known as Hubbard model. We consider this on-site interaction term. Then uh, we can calculate the correlators as shown in the figure. So this figure, the dependence on the different sites is mostly centered on the very first atomic site, and all the correlators related to the from the nearest to the farthest, we can plot them as in the figure. So you can see that in the metallic phase, electrons can move more freely. However, in the insulating phase, when you introduce the interaction, it becomes more insulating, and this phase is known as Mott insulating phase. And then in the insulating phase, the electrons cannot move so freely. So this long-range correlators will suppress very quickly. This is natural to think. Of course, we can. This is only for the very first site. We can also consider plotting the other correlators in this chain, but it will be not so easy to understand what's going on. So we do the another way. These are the correlators that involved in this plot you are seeing. And then this is we put all the correlators in a row, and we don't forget another spin component. And we can consider the second atomic site. We do the same, and so on until we cover all the correlators. Then we have a matrix. This is an example of 8-site as a Hubbard model. So our correlation, this matrix will have a 2n by 2n site, which is 16 by 16 site, and we call this matrix as correlation matrix. So we are all physicists. So when we see a matrix, we always want to find its eigenvalues. This is exactly what we did. And when you find the eigenvalue of the correlation matrix, you find something very interesting. In a non-interacting case, the eigenvalues are either 0 or 1, while the interacting case, it ranges between 0 and 1. That is very important and useful because you can define an entropy-like a quantity in the following. We call it a correlation entropy, which is always 0 in the non-interacting case and finite in the non-interacting case. So we get the first intuition about the correlation, this quantity, call it correlation entropy, and which is, we can use it to distinguish our system, whether it's interacting or non-interacting. But it is more than that. Let's consider, add one more term to our Hamiltonian, so make it a bit more complicated. This term is a nearest neighbor interaction term. So this is called extended Hubbard model, and it is known as its rich quantum phases in the UV parametric UV phase diagram. And you can see that we can calculate this correlation entropy. I've shown you how to calculate the correlators with DMRG, and then we can just calculate all the correlators in our system and find its eigenvalues, and we get the correlation entropy. We calculate the correlation entropy, and then we get something interesting. So there are a couple of phases included in the phase diagram of the extended Hubbard model, and with correlation entropy, we can nicely distinguish these phases. But however, let's see, you need to pay attention to something very important. This is, according to the known phase diagram of the Hubbard model, this is called charge density wave. Charge density wave is known as, it's known as product state, which means if you take the subsystem of the charge density wave, so these subsystems are very much independent from each other, which means there is no entanglement. So actually, we can have a further definition of the correlation entropy. So it actually measures how a system is away from product state. In this sense, it's better because a non-interacting system can also be considered as product state, and then uh, which means there is no entanglement. So in fact, a correlation entropy actually measures the complexity of a quantum state. So it means how much, how complicated, how many entanglement involved in a quantum state. So
So you have a choice to look at any state. So is this psi just the ground state of this extended Hubbard model?
yes, yes. This density DMRG method is mainly used for the ground state of the many-body system. Yeah. So when I have worked with so far we have 3 papers with correlation entropy, and then every time we submit a paper, we get referees talking about von Neumann entropy. Obviously, this is a very confusing for some cases because a lot of people are using von Neumann entropy as the measure of the entanglement in a system, so it's very easy to get confused. So uh, the von Neumann entropy is well known, and the people are using it as a measure of the entanglement. So it multipartite the system. For example, this example I'm showing you is the on-site von Neumann entropy, which means it is 1 over n multi-partition of the system. So it only concentrates on if you have 8 systems that just take one of the side and calculate the von Neumann entropy of that site, which is completely depends on the reduced density matrix. So, however, the correlation entropy is a bulk property, which is completely different from the von Neumann entropy. We consider all the correlators involved in a many-body one-dimensional fermionic chain, let's say. So here is also another advantage. You can see that the von Neumann entropy, even when the interaction is zero, the von Neumann entropy is still finite because you're artificially multipartiting your system. You're considering it subsets of the whole system. So that will make the von Neumann entropy is always finite. However, the correlation entropy as a bulk property, if there is no interaction, then there is no correlation entropy. It's always zero without interaction. Another thing you can already see is that if we make it a correlation entropy per side or correlation entropy density, then it will be almost size independent. I'll come back to that shortly. So let me summarize a bit the very basic features of the correlation entropy. First, it measures complexity of a many-body state, which means it represents how much a many-body state is away from product state, which means like also means it can measure the amount of entanglement in a system. And then as you can see in the phase diagram, we can also use it to distinguish many-body phases in a specific problem. And then another thing is the extensive scaling. So in previous case, it's just a simple Hubbard model, but we can make it more difficult. We add a lot of terms to our Hubbard model. Let's see if is it still extensive? So yes, the answer is yes. Even our Hamiltonian is very complicated. It can still be this correlation entropy per site can be still be size independent when the system is large. However, that will also bring another problem, that its size. In the previous case, the very complicated Hamiltonian becomes size independent at 24 site. That means the size of the correlation matrix is 2,304 correlators. In theory, yes, we can do it, no problem, but we cannot ask an experimentalist to measure 2,000 correlators to get this one quantity. That's why no one has ever measured this correlation entropy so far. It has been studied from the 1970s, but no one measured it because the number of correlators are just too much to determine this correlation entropy. So the first question is, can we use machine learning to make it work, make it accessible from experiment? So let's come back to the basic question, how? So this heat plot is the correlation matrix. So you can see that it has some good properties, which it has some patterns in terms of correlators. These colors is just correlators, how big or how small they are. And then the diagonal elements are always the same number because they're number operators. And then the initial aim is, can we determine the correlation entropy just from a handful number of correlators? For example, you just take take a block of it, and central block is good because we're considering a finite sized system. So if we take the correlators from central block, we will reduce the finite size effect. So can we do this? The first thing to do is check, can we do it without machine learning? But however, this idea is already very similar to the von Neumann entropy. It's just multipartiting your system and then considering it from the center of the chain. So obviously the answer is no. You cannot use a fraction of the system or a small block of the system to determine a bulk property. However, so which means in this heat plot, you can the long range correlators are not so much visible, but they matter. The information we get from the results are these long range correlators matter. If we want to do machine learning with local correlators, like I'm labeling in the heat plot, we need extra help. So we use call it density correlators. So with this density correlators plus the local particle correlators just related to this extracted from the central block, then we can determine the correlation entropy with deep learning method. Like you can see that these black dots in the figures are very well matched. So how did we do it? So we have, as I mentioned, we have this particle correlators. And we also have this density correlators, which are also local. We just consider one-dimensional chain. We put our attention to the central side because we want to reduce the finite size effect. We extract the correlators related to the central side. So far, in most of our papers, we only consider 4 central sides, no matter the system size. We just use 4 central sides, take all the correlators related to this 4 central site, which is not all the correlators related to the 4 central site, but the most relevant ones. For example, each particle and density correlators are about 36. So altogether, our input data will be 72. Compared to 2000 correlators, 72 is just a piece of it. And then we develop our neural network structure. We do use a pre-processing method like normalization, PCA. And then PCA is sometimes helpful depending on the system, because if your system is not so much spin dependent, for example, you will have correlators like spin up, spin down, and this will be 0 if your Hamiltonian doesn't include this kind of terms. So when you use PCA, you can just exclude this kind of contributions in the data. You can just reduce its dimensions. And then the dense layers, usually we use 3 layers from 500 to 1,000 nodes from for each layer, and then we can just make the prediction. So then we use this quantity called fidelity as our measure, and then we use fidelity to measure accuracy. And then one thing we also noticed is if you keep increasing the examples, let's say, to extract these correlators, at the end the accuracy will saturate, so it will not keep increasing as if you just use more data. The reason is also simple, because even you provide a very rich and a diverse data set, these correlators may the correlation information extracted from these correlators will be similar, too much similarity, then the accuracy will not increase if you have too much data. So this is actually the Hamiltonian that I considered in my very first machine learning paper. We solve it with the DMRG library written by one of my supervisors, Jose Lado himself. And then we use this Altos computer clusters, use its computing power to calculate it, and also calculate the correlators, the correlation entropy, extracting the correlators, and so on. Everything is done there. And then for machine learning, we use TensorFlow. After that, we can develop our machine learning algorithm. And then the one example, what we can do here is, this is the extended Hubbard model I showed you earlier. It has rich faces, so it can predict well, because this Hamiltonian, the extended Hubbard model that we are going to predict, we are going to predict the correlation entropy of this extended Hubbard model, which is a subset of the Hamiltonian that we are extracting the correlators. So this works because it's a subset of the data extracted from this target Hamiltonian is just a subset of the data that we extracted the data to use for training. So even the data is unseen, we can make good prediction. This is our very first machine learning paper. So the
I have
next
a question about that.
Yeah,
So just to be clear, what happens at inference time is that you provide it with some small number of entries in your correlation entropy matrix, and then it
Yeah.
populates the rest.
Yeah. No, it does not populate the rest. It uses the small finite amount of correlators to predict the correlation entropy. Of course, we calculate the correlation entropy beforehand, and before we train. But after we train, then
I see. So you don't get the
Yeah.
detailed matrix, but the just final correlation.
Yes, that's the very idea. We just back engineering the whole process with a finite number of correlators. And the density correlators is actually not included when we calculate the correlation entropy, but it helps to make the prediction, make it more accurate. That's the whole aim. Yeah. We skip the process of calculate the full correlation matrix, so that if experimentalists want to measure the correlation entropy, they can just use local correlators, both particle and density correlators, to make this prediction work. That's the idea.
If we have long range correlations, though, do we expect a good prediction for the correlation entropy?
You see that this our Hamiltonian actually is a bit too much complicated. We have on-site interaction, nearest neighbor interaction, and then in the first slide, you have seen how the correlators propagate along the system, which means long-range correlators, how they behave. The answer is yes, it works. It works very nicely. Because we included the density correlators, which are also, in fact, they're not long ranged, but they're also, like, we extracted them from also local correlators, but they provide the different information than the particle correlators. That's why that's the reason why it works.
Okay.
Yeah, this is the first machine learning paper we worked on, and then it worked very well. So the next question comes is, okay, we add a term to our target Hamiltonian. It is spin-spin interaction. And then this term, when we extract our data from the full Hamiltonian, the very complicated Hamiltonian, this term is not included. But now, if our target Hamiltonian this data is this term is there. Can we make this prediction? The answer is no, because the spin-spin interaction like this will introduce ferromagnetic order that is not included in the source Hamiltonian. So the algorithm we train it on with this long Hamiltonian does not include any information about the ferromagnetic order. It's all about antiferromagnetic order, so this will never work. So let's see why. So let's consider two very simple cases. So left side is the Hamiltonian with the Hubbard term and plus a next nearest neighbor interaction. And then all other terms are zero. So the right one is we do have finite chemical potential, but all other terms like T prime and including T prime are all zero. So you can see that how the correlation matrix heat plot looks like. They look quite different. That's why if you didn't include this term, that's for example, you didn't include chemical potential on the left Hamiltonian, you will never, if you train it with millions of examples, you will never predict the correlation entropy of the system on the right. So you may ask, how about your density correlators? We are also using it. That's true, but it's actually even worse because you can see that they look quite different. So particle-particle correlators, we are using to calculate the correlation entropy, but they look quite different. We cannot do much about it, but can we do more with the density correlators so that they work, so that we can predict some Hamiltonian that some of it's not because when you see some new when you add new parameter to your Hamiltonian, it introduces new phases that is different from the phases that you train at your data. So can we make this work? So we did some tricks. First is we exclude the Hartree-Fock approximation. So if in the non-interacting case, your two particle correlators will look like this. You can expand it in terms of the Hartree-Fock theorem. And then in the interacting case, then you can just subtract these two particle correlators from the many-body version, and then which applies to our density correlators, make it that in the following way that you are seeing on the screen. Another thing is I already mentioned it, that the diagonal terms will always be the same. Just keep away from the diagonal terms in the data, in the correlation when we extract the correlators, and then that will improve our accuracy. Now, after doing these tricks, let's see how the density correlators look. They look good. They look much better, and they look similar, even though these two Hamiltonians, the two versions of the extended Hubbard model, one with only next nearest neighbor hopping, the right is only with chemical potential, finite chemical potential. So they're completely different versions of the extended Hubbard model. They look quite similar, which means that these density correlators will help us to make such move. So what we're going to do is we're going to test different algorithm on different versions of the Hubbard model to see which case works, which case does not work. So the first case is we get our correlators from the pure Hubbard model. H0 is just a pure Hubbard model, and we train our neural network algorithm there, and we make predictions on unseen data. Of course, it's unseen now that because the prediction is made on various versions of the extended Hubbard model. So what we are doing is we are using just using one algorithm, which is completely different in phases to predict on the correlation entropy on the different version of the extended Hubbard models. So we can do next, we do have, but then we add a chemical potential to our system, to the pure Hubbard model. So now you can see that the first element, the fidelity will be just one, because even the data is unseen, but this data is quite similar. So the first in the second row, the first element is first value of the fidelity is always one, and this is the very much the thing that we already done in our first paper. But the rest component, the rest value in this row will be quite different, and so on and so on. We consider also this. We change sign of the chemical potential and so on. I add more terms. So what we are doing here is uh, we are not only predicting unseen data, we are also predicting unseen parameter regimes, which means we are training on one data set and predicting on uh, another data set that is not only different in the parameter space, also like it means also predicting on quantum phases that are not seen in the training process. So we want to find the model that we want to develop an algorithm that when a new term when a new data comes, even this data is not seen, the source of the data is not seen in the training process, we can still able to make this prediction. We are looking for this specific algorithm. So this is the main result of this work. So you see a lot of light colors, which means good, which means this transfer learning algorithm is actually working. So you see some darker colors which are not working well. So which are these three columns here. So this spin-spin type of interaction will introduce ferromagnetic order. I already mentioned earlier. And then this lambda r is Rashba type spin-orbit interaction. And then these three columns are fundamentally different from the rest of the columns, the rest of the columns are antiferromagnetic order. So, which means this kind of transfer learning will never work if we are talking about we are training on one data set based on some kind of Hamiltonians, and then we are predicting on different data set based on some different kind of Hamiltonians. If these two systems have different quantum orders, like fundamentally quantum orders, like this antiferromagnetic, ferromagnetic, or spin orbit coupling, then this method will never work. So this is the first thing that we can learn from this table. And then let's see some examples. Let's take this Hamiltonian and see how it looks. So the data is the algorithm is trained on the data extracted from Hubbard model with chemical potential. So it can predict well on every single case. The most trivial is actually the A subplot, because we just changes the sign of the chemical potential, and then when you change sign of the chemical potential, it does not do much. It's just the correlation entropy is symmetric under mu, so it can predict well. This is very trivial. However, this is the most non-trivial case is the UV phase, because you see that there are quantum phases that are not included in our training data set. For example, bond order wave. This is like this is a hard one to be accessed in both in theory and experiment, but here the correlation entropy can access it. And the most important thing is our training data set never included that kind of order that UV can introduce, because we in this algorithm, and that when we train it on, we don't have V in our system, but we can predict the UV phase diagram very good. In fact, to me, the predicted UV phase diagram looks even better than the calculated one. Also the charge density wave, because in the original data set, the correlation entropy will only be completely zero if U is zero. So you see the metallic phase, it's just it's not completely zero. You know that the correlation entropy values change smoothly from zero to some finite values. But charge density wave, the correlation entropy is completely zero. So these are also like the charge density wave is also not seen in the training set. So this is the thing that we wanted to see, and it is working in a way. Yes, we are reaching this kind of prediction that even the data we extracted from our original Hamiltonian is and it can predict some systems that these quantum phases are not visible in the training set. So let's also use this model to see the ones that didn't predict very well, which is the ferromagnetic phase. And as you can notice, the ferromagnetic phase is if we just change the sign of J from antiferromagnetic to ferromagnetic, it will not enter the ferromagnetic phase right after. It will have this the ferromagnetic phase will appear at within some value of J and U. So the antiferromagnetic phase is predicted well with this model. However, the ferromagnetic phase is completely zero because it's completely gone wrong. However, it's pretty obvious that even the prediction is very wrong, we can still qualitatively distinguish these phases. That's why the fidelity is very low in that table, but the phase itself is not so bad. We can still distinguish it. So the summary is yes, with this transfer learning method, with the tricks that we use it, we can indeed can predict not only unseen data, but also the unseen. We can also predict on unseen parameter regimes, which introduce completely unseen quantum phases that is completely different from the phases included in our training set. So these bar plots are actually the summary of the main results, that the fidelity table that I showed you earlier. So you can see that most of the fidelity values is like it's right skewed to 1. So which means if we just zoom in, like even half of the algorithm predictions, like the fidelity is exactly at 1, which means very good. And that the rest, even the fidelity is not so good, as you have seen in the example, we can still qualitatively can determine these quantum phases nicely. Let's come back to this fidelity table, as it is the main result of our paper. So that one in all algorithm that we don't need to retrain. Actually, we find two candidates for this. This chemical Hubbard model with chemical potential. It has only two phases from metal to insulator transition, but it can predict well on different unseen phases. As long as the fundamental quantum order is antiferromagnetic, this algorithm works very nicely. Another candidate is the Hubbard model with Rashba spin orbit coupling. It also predicts very well result. It also can include of course, it can predict well on the data. It includes Rashba spin orbit coupling, but also can predict others as long as it is not ferromagnetic. Okay, so that will reach my final conclusion of the paper.
I have a
So,
question.
yeah,
If you
yeah,
go back,
yeah,
when you're producing this table,
yeah.
how many different parameter combinations are you examining for each category? Like maybe row and column. Like essentially, I'm trying to get a sense for the importance of task diversity in
yeah,
of
yeah.
transferability.
So when I say H mu, H0 is the pure Hubbard model. There is just hopping and the on-site interaction, right? So when we say H mu, add the chemical potential term on top of H0, which is the pure Hubbard model. And if we say HT prime, we add nearest neighbor hopping on top of H0. There is no mu or nothing. It's just H0 plus HT prime, the term nearest neighbor hopping,
I
and so
see. So
on.
you're turning on
Yeah.
like one type of
Yes.
interaction or term at a time. And then how many examples of each do you need in order?
When we train our machine learning model, each example, I try to use 20,000 examples. If you remember in my previous slides, uh, some were like it will saturate if you include too many. So 20,000 is already like pretty nice accuracy we can get. Um, I'm also afraid that if we generate too much data, that in the test set it could be also uh, if you want to generate test set, it could also include some data is very similar to the training set. That's why I only consider 20,000
Mhm.
examples for each. And then of course the predicting the data is also completely generated, randomly generated examples. Um, so that's why it's unseen. That's the idea. Yeah.
Okay, thank you.
Yeah. So the final conclusion is uh, correlation entropy is a very good quality, as I summarized it earlier. We can use it to determine a lot of things. We can use it to study the various features of the many-body system. And then for its determination experimentally, we did provide this neural network algorithm to use local correlators to determine the correlation entropy. We went further in our recent work so that we don't have to retrain every time when we add a new term to our Hamiltonian. We have good candidates for this as long as our system is not ferromagnetic. Then we can make this prediction work very well. Even we have seen new terms. Even you add like a couple of more complicated terms, it will still work. So we don't have to retrain. This transfer learning is also working. So, and we also believe that this 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 method is very useful. This kind of transfer learning method is very useful for similar other problems as well. Yeah, and then I thank my both supervisors, Temo Ojanen at Tampere University and Jose Lado at Aalto University. And thank you very much.
Okay.
That would be it. So if you have any questions, I will be happy to answer.
I have a couple of questions.
Yes.
So you're making these plots using the entropy density, and I'm imagining that in order to train the algorithm, you need to be able to do the DMRG, so you're limited
Yeah.
in system size. And I'm wondering if you did any scaling analysis of the performance as a function of like system size. So, for example, if
Yeah.
I now want to use something that was trained with one system size to predict these, correlation entropy, diagrams for a really large system size that I, cannot get the answers for with DMRG, how close can I get, maybe?
Um, Actually, I forgot to include this results. Actually, in our recent work, in the referees asked the same question, like, can you really generalize it? Because where is my that slide that showing it is this correlation entropy per site is actually yes here. The correlation entropy per site uh, you just calculate the correlation entropy and divide it with the system size. It's some kind of definition of the density or correlation entropy per site or however you define it. It is independent from system size. It's a good thing. And then if you, we did, I'm talking about 24 site, but we trained our model on 32 site. in all the papers. So which means uh, when we extract correlators from the central part of the one-dimensional fermionic chain, so they're far away from the two ends, which means the finite size effect is already very small if we consider 32 side. So in the appendix of this paper that just got accepted, sorry, I forgot to include in the presentation that we did predict, we used 32 side to train our model, and we predict on 24 side, 40 side, 48 side, and it worked all well. We can predict it correctly, no problem.
Okay.
So I hope I answered your
Yeah, yeah.
question.
I also have another question, which is, do you have any explanation for why it's good at predicting the phase boundaries, if not the actual phases?
I actually I think it can actually predict the it can I feel like it can actually predict the phases good.
I meant in
Uh,
the case where you have different like type of order.
yes, you mean the transfer learning.
Yeah, yeah, yeah.
Yeah, I think these are actually very good examples. Sorry, I also forgot to actually post the density correlators in the of the ferromagnetic phase. So they even you do these tricks, do this extracting the mean field contribution in the density correlators. Uh, the local correlators still look so much different in the ferromagnetic case. It's so much different from the antiferromagnetic case. So the machine learning we develop our algorithm. It learns from the left correlators, for example, and then it trying to predict right. This is the transfer learning concept. But they look similar. That's why it works. However, in the ferromagnetic case, it looks so much different. Uh, Sorry, this is the one that it does not look different. It does not look the same. So it does not look, if it does not look the same, so it will never work. That's why. So that is the deep reason behind it. I mean, more mathematical or computer uh, s- uh, perspective. It's the reason why it didn't work.
Well, in a later plot, I think if you scroll down, if I got this correct, you were making the argument that it got the boundary correct, even though it got the actual value.
Yeah, yeah, yeah. Yeah, this one. Yes, you can see that J, this parameter, introduces ferromagnetic order. And if you just flip sign, I mean, it depends on how you introduce. Like if my term has a minus sign in the Hamiltonian, then plus J will introduce ferromagnetic order, right? Now I have a plus sign in Hamiltonian, so minus J will introduce ferromagnetic order. So it will, if you just change the sign of J, it will not introduce the ferromagnetic order immediately. It introduces ferromagnetic order in some parameter range. And then uh, you can see that the prediction is so wrong, but we can still see the differences in the ferromagnetic phase. You can still differentiate. This is so much different, right? So this is the thing that we learned. Because in the ferromagnetic region, as I said, the correlators are so much different, the algorithm confuses. The algorithm thinks, okay, uh, this is something that I learned, but however, it's not learned that. That's why it makes wrong prediction.
Do we have any more other questions? All right, let's thank our speaker again.
Okay, thank you so much for your invitation again.
Yeah, thank you.
Thank you. Have a nice day.
Yeah.
Yeah, so I think you already